Science is about explaining, not about describing. Math is a descriptive language. It can only describe. I can tell you how fast something runs. I can tell you how fast, what the acceleration of gravity is. But I cannot explain to you what gravity is or how it does its magic. For this, there's only one way. You have to try to figure out what invisible object is doing the mechanism. And that's what I'm going to explain today. I'm going to do it with black holes. I chose the black hole because the black hole is like the ingrown toenail, the smoking gun of relativity. It's as irrational as it can get. If you can't get past the irrationality of a black hole, I'm wasting my time today. I should pack my bags and leave. If I can't make my case today with a black hole, I got to leave. I have nothing more to offer, okay? I called my presentation, The Rope Hypothesis Rationally Explains Dark Matter, Black Hole, and Big Bang. And I'm going to go through 4 steps here. The first one is I'm going to argue that there is no such thing as a black hole. You read about black hole every week, that they discovered one, that they saw one, that they proved it, whatever. And I'm going to argue that there's no such thing as a black hole. Why? Because you heard of impossible objects. Okay, you got the tri-bar, you can't produce this in 3 dimensions. You've got the Penrose staircase, the impossible cube. You have all these things which are known as impossible objects. They're irrational objects. And that's where the black hole belongs. It's an irrational object. Okay, that's what I'm going to show today. Then I'm going to go in there and explain phenomena that currently is attributed to black holes, and I'm going to give you a totally different scenario. You're going to see with your own eyes a different perspective. Now, I haven't come here to convince anyone. I haven't come here to persuade or recruit anyone. I just want to give you something that you can compare and make your own decision. That's the way science should work. We should not shove down your throats a theory and say, it's been proven, we have the truth. No. I explain, you understand, we're done with science. What continues now is religion. I'm going to explain phenomena attributed to black holes. Then I'm going to explain a phenomena attributed to dark matter as well. And finally, I'm going to argue against another icon of relativity, which is the Big Bang. I'm saying it never happened. There was no beginning to our universe. Okay? So on with the first one. There's no such thing as a black hole. What is a black hole? What is the definition of a black hole? When you look up this term, what are they talking about? That's the first one I'm going to go through. Then I'm going to go through how many dimensions a black hole has. We're going to find out the black hole has many dimensions. What is a black hole made of? I think it's a rational question to ask. If it's a physical object, what is it made out of? Have we ever discovered a black hole? Have we ever seen one? Have we ever proven black holes? And I'm going to get testimonies, official testimonies on that. And finally, if we have not proven the black hole, then we have to conclude that maybe the black hole is beyond human understanding, and we have to accept it like we accept other religious things on the basis of faith, authority, or whichever one you want. Okay? So on with the first one. What is a black hole? Well, when you do some research, very light research, you find out that the black hole has essentially 2 definitions. There's 2 notions of a black hole. On the one hand, you have the black ball, and on the other one, you have a region of space or of space-time. So you have these 2 notions. We have NASA treats it like an object, as a black ball. And here's the testimony. This is directly from these websites, right? Black hole, a great amount of matter packed into a very small area. They're talking about small, not 0 dimensional, they're talking about small. Think of a star 10 times more massive than the sun squeezed into a sphere. They're talking about a sphere, they're not talking about 0 dimensional. Approximately the diameter of New York City. Diameter, again, something, right? Greater than 0. Gravity is so strong because matter has been squeezed into a tiny space. Again, all the representations, you're talking about something. There's something that has size, diameter. They're talking about a black ball, okay? Wolfram physics treats it as an object. Space.com, two lines there only. Relatively small, you see it there, and city size range. So again, they're all talking about something, a little ball of some kind. The star shrinks and turns into a ball, not into nothing, but into a ball. And then we have the other side, where they treat it as a concept, a region of space or of space-time, depending on who you talk to. And Berkeley says it's a region of space, but the good one comes from Max Planck Institute. It says a black hole is not a tangible object. Making it clear, you're not talking about a ball, you're not talking about a tangible object, but it's a region of space. It says later on, it says black holes themselves are not solid objects. They said object, okay. It's not a solid object. There's nothing there. Okay, so we have these two notions. Now, there's a difference between a ball and a region. Now, I know some of you are not from this planet, so I'm going to show you something that is from our planet. Our planet is Earth, and this is the mysterious black ball, okay? Now, black ball, can you all see this? Yes? Why can you see it? You can see it because you have light reflecting to your eyes, or the ball is emitting light to your eyes, some signal, and you capture it with your eyes, you see it. But before you can do that, there's got to be a precondition. And the precondition is the black ball has to have shape. If there's no shape here, there's nothing to reflect light to you, there's nothing for it to emit, because there's nothing here. But here you can see it. Now this is a region of space. You can see it here between my two fingers. In fact, I'll take my fingers out so you can see it better. Do you see anything there? How can a region of space send you any signal? A region of space is not a physical object. It's not the same thing as a ball. So these people have two different notions, and I synthesize it here. What does a region look like? Have you ever seen a region? Can I bring a region to you like I brought the ball? I can bring a chair. I can bring you a table, a tree, a rock. I can't bring you a region because a region is always of something else. I can talk to you about the region of the ball, but I can't talk to you about region just itself. In fact, I can do something else. I can show you my hand. I cut my hand off of the wrist, and I can show you my hand. And I can talk to you about the palm. The palm is a region of the hand. I can talk also about a palm, but I have to cut the fingers. So I cut the fingers off, I show you the palm, say this is a palm. So far, so good. But if I want to talk to you about the palm being a region of the hand, I got to sew the fingers back on, because a region is always of something else. And now you have the very funny conclusion because of this, these two notions, region versus ball, we're in Mexico. Let's use a Mexican citizen. We take a Mexican citizen from the streets, we crush them, we smash them, we make them as small as possible, and we turn them into a region of Mexico. Sounds like a plan? That's what they're doing. They're taking a star, they're shrinking it, here's a standalone object, and they're converting it into a region of space-time. What sense does that make? Right there, they have, first, a contradiction in the definitions, and second, they draw these conclusions that a standalone object becomes a region of something else. Makes no sense whatsoever. Okay, how many dimensions does a black hole have? Well, one of the persons who most worked on black holes originally was Chandrasekhar. He was an Indian student who went to Great Britain, and he became famous, eventually got the Nobel Prize because of his work on black holes. This is what Chandrasekhar said. There is a limit to the repulsion that the exclusion principle can provide. When the star got sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. It would collapse completely. Eddington, who was his boss, nixed that. He said, no, I'm not going to let you continue in this line of work. He thought it was simply not possible that a star could collapse to a point. And this was the view of most scientists in those days, and Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. And then Chandrasekhar wins the Nobel Prize, and he had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. And that's in A Brief History of Time by Stephen Hawking. So this is official, this is the current thought. So here we have a star, collapses to nothing, to 0 dimensions, okay? Here we have the BBC. They made a documentary in which another rising star, Brian Greene, says something different. He says the black holes are collapsed stars, massive objects crushed to a fraction of their original size. Now this is not zero dimensional. Now they're talking about fraction and size. So again, we have these two versions. Which is correct? Does a star collapse all the way, or does it remain as a ball at the end? So he's representing the black ball, whereas the testimony just now by Stephen Hawking is that it's nothing. It's zero dimensional. So we have zero dimensional and three dimensional. Someone asked the question, how many dimensions does a singularity have? And several of the mathematicians, not physicists, gave answers. I picked out two because they addressed two separate issues. The first one said, the concept of a singularity is a mathematical concept, not a physics concept. And this is funny because we have constantly, in fact, I think I have it here. In the string theory, it says it very clearly. The language of physics is mathematics. So it's the language of physics is mathematics. Here they're saying something different. They're saying the concept of a singularity belongs to mathematics. It does not belong to physics. So we have a contradiction. They go around in circles. You say, well, how many dimensions does a black hole have? They said X. You say, well, but that's mathematics. Yeah, it's mathematics. It's got nothing to do with physics. And then they tell the astronomers, go look for it. Now they're looking for something in the sky. What are they going to look for if this is a mathematical concept? We have these contradictions constantly over and over. And a second answer which I picked, it says if we think just in terms of space, it's zero dimensional. But in a space-time, it is one dimensional because it exists over a period of time. So now you're saying, hold it. Black hole collapses to a zero-dimensional point, nothing, right? And that's what you get on the 3D space side, right? Head-on view, you see nothing, zero-dimensional. What are you going to see? But then if you see this in time, now you see a movie, this zero-dimensional point traces a one-dimensional line which comes out of the other side in another universe as a zero-dimensional entrance. Now, have any of you tried to enter a zero-dimensional entrance ever in your life? Have you ever tried to crawl through a one-dimensional line? This belongs totally in mathematics. What does this have to do with physics? It has nothing to do with physics, but they go around and around and around. How many dimensions does a black hole have? I can tell you right now. It has zero-dimensional if you're talking about space, right? Right there it says so. It has one-dimensional if you talk about space-time. It has two dimensions if you take a ball and squeeze it down to like if you project it onto a two-dimensional platform. And it has three dimensions if you're going to look for it with your telescope. So how many dimensions has it? It has 0, 1, 2, and 3. There's your answer. They covered every base. Luis Lehner and Franz Pretorius, these guys published a paper saying, we showed, this is a peer-reviewed paper, this is official, the black hole's radius is 0. Very clear. There's no radius, there's nothing there. That's not what they draw. Look what they drew. They talk about, I hope all of you can see that black dot in the center. That's two-dimensional at least. It's got width and height. And that's a representation of a three-dimensional ball. So we have 3 dimensions, 2 dimensionals, and these guys are telling you it's zero-dimensional. So which is it? And that's just the dot in the center. If you talk about the event horizon, which is the so-called limit, the region of influence of a black hole, now you're talking about at least 2D and 3D. So what they draw, physics, has nothing to do with what they publish, which is math. They publish math, and then they talk, and then they draw or illustrate physics. Two different things. And then again, someone here says the radius of an event horizon increases as the mass of the black hole increases. Now we're talking about radius, we're talking about size again. So they go back and forth. So what's the problem with all this? Well, the problem is that in physics, when they want to talk physics, when they want the common man who doesn't know anything about mathematics or what these guys are referring to, they say, look, that's a black hole. And everybody can relate to it. He says, yeah, I understand what they've got there. It's some kind of tornado. And it swallows stuff? Yeah, I understand it perfectly well. But that's not what they publish. This is what they publish. When you look at the papers that they publish in the peer-reviewed journals, they talk about zero-dimensionality. They put their equations there. It has nothing to do with what they show the public. So we don't know how many dimensions have, but in fact we do. They have 0, 1, 2, and 3 because they covered every base. You can't challenge this anymore. What are black holes made of? That question was asked of these 4 gurus of physics. I call them mathematicians because they do everything with magic. Michio Kaku, he just shrugged. Larry Krauss also shrugged, he didn't know. Andy Strominger, he's from Harvard, professor from Harvard, he says, oh, okay, already you've asked me a question I can't answer. And Max Tegmark, another rising star, said, we don't really know what's going on. These were the official responses. Now, there's a problem here because these are college professors. These guys studied at least 10 years in the universities. They have PhDs, okay? And now they tell you, well, we don't know what a whole black hole is made of. What do you mean you don't know what a black hole is made of? Let me show you what a black hole is made of. Black hole is a region of space that has much mass concentrated in it. A black hole is all mass and no body. It's very simple. Black hole has mass. Why didn't they answer that question? They should have said, oh, it's made out of mass. And then maybe they opened up a can of worms if they said that, because if they say, look, it's made out of mass, and you say, well, what do you mean it's made out of mass? Well, what really is that? And here's the problem. The no-hair theorem says all black hole solutions can be completely characterized by only 3 parameters: mass, electric charge, and angular momentum. And the Wikipedia clarifies that the simplest static black holes have mass but neither electric charge nor angular momentum. So no matter what black hole you deal with, it has mass. Some have angular momentum and charge, some don't, but all of them have mass. Why didn't they answer that question, these college professors? I'll tell you why. Mass is the quantity of matter of an object, or it's a measure of the quantity of matter. That's what you learn in high school or college. But the black holes crush matter out of existence. There is no matter in a black hole, which is the definition of mass, the quantity of matter. So we have a circular definition. We have a black hole is made out of mass. Mass is the quantity of matter, but a black hole crushes matter out of existence. So what do we have in the end? We ended up where we started, 0. We have nothing. So what do we have? Do we have a ball? Do we have 0-dimensional singularity? Are we talking physics? Are we talking math? This is the problem. But if you think that's the end of it, no, there's one more step. Here are these other 2 gurus, John Wheeler and Edwin Taylor. Nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count the number of atoms or by any other counting method, try to evaluate amount of matter, that number would not equal mass. Mass is not the quantity of matter. They have no clue what mass is. They don't have a definition. So after we went around in circles, we find out that mass is really not the quantity of matter. So we have several problems here. We have first 2 definitions. We have the region and the ball. Then we don't know how many dimensions it has. In fact, it has all the dimensions because they covered every base. What are you talking about? You talking about space? Oh, it's got 1 dimension. Oh, you're talking about space? No, it's 0 dimension. So you don't know what are they talking about. And then they say, they go around in circles and tell you that, a black hole is made out of mass. Mass is the quantity of matter, and matter is crushed out of existence. What have we learned? What is a black hole? This is the irrationality of black holes. And they put it out as proof. Okay, let's find out proof. How do we stand on proof? Have you ever seen a black hole? They ask these same people. And they say, no, I caught them in the moment. They say, no. No one has ever seen a black hole directly. So how do they prove it? I mean, it's proven. It's a fact. We see it every day in the popularization magazines. And now they're telling you, we've never seen a black hole. Well, hold it. Just 10 days ago, 11th of February, big news. We had the LIGO, some people call it LIGO. LIGO, this is a group that for many years, since the 1990s, they've been looking for gravitational waves. They finally found 2 black holes that came together that emitted the gravitational waves. Oh, we've proven it. We've proven it. We're the first. These observations demonstrate the existence of binary stellar mass black hole systems. This is the first observation of a binary black hole merger. And immediately someone in the Wikipedia put it, on 11th of February 2016, the first ever direct detection of black holes was announced by the LIGO collaboration. Well, these people are out of touch. We've been proving black holes at least since 1988. And I brought proof. This is from Stephen Hawking's book, A Brief History of Time, 1988. I have done a lot of work on black holes, and it would all be wasted if it turned out that black holes do not exist. Very powerful reasons for making them exist. In fact, he had a bet with another college professor. His name is Kip Thorne. And he said, look, if Cygnus X1 turns out to be a black hole, I'm going to buy you, what was it, 1 year subscription to Penthouse magazine. And he finally said, I had to concede the bet because all the evidence shows that Cygnus X1 is a black hole. What else could it be? And he adds, we also now have evidence for several other black holes in systems like Cygnus X1 in our galaxy and in 2 neighboring galaxies called the Magellanic Clouds. So they have all this evidence, and now they say, oh, we've discovered it for the first time. Well, we've been discovering for a long time. In fact, I'll show you more evidence. Physics World, this is 2011. Famous black hole confirmed after 40 years. Another one, this is 2012, January 2012. The very first black hole ever discovered was discovered at U of T. November 2012. Scientists baffled by huge black hole discovered in tiny galaxies. They've been discovering black holes every month. The first one, always the first one. Monster black hole spin revealed for the first time. So what are these people talking about? What do you mean the first one? They had to give jobs to LIGO because these people hadn't discovered anything in 25 years. They spent $600 million. They didn't discover anything. And now at the 100th year anniversary of Einstein, they said, we finally discovered gravitational waves. And everybody pulled out the champagne bottles, among them Stephen Hawking. He was given an interview. He gave an interview. And he said, oh, this is a great find. We've finally discovered black holes. What do you mean? You've always discovered black holes. And how can he say he discovered black holes if he's never seen one? Has Stephen Hawking looked through the scope and seen something? No. Someone else did. So he's taking their testimony and putting it as his. He's not an expert witness in this. He's never seen a black hole in his life. Why should I trust his word? Has he ever seen one? Can he bring me a black hole? Can he draw a black hole, a zero-dimensional singularity? He's never seen a black hole, so he's not an expert witness. An astronomer might be able to tell me, yeah, I've seen one. Okay, but not Stephen Hawking. What are they doing? They're using his authority to convince you, the public, oh, if Stephen Hawking says so, it's law. He's not an expert witness in this trial. He shouldn't be called to trial. So they asked the astrophysicists at NASA, who was the first person to discover a black hole? And they answer, black holes cannot be observed directly and therefore cannot be discovered. They only look at it through indirect evidence. What does this mean? It means they're not proving anything. They're making an assumption. They're saying, let's assume there's a black hole, that black holes exist. We see something, what could cause it? It must be a black hole. That's an assumption. That's not a proof. And they're turning their assumptions into proofs, into facts. That's what they're doing here. What? To convince the public, to say, look, we know what we're doing. But they can't define it. They can't tell you how many dimensions it has, but they've seen it and they've proven it. We got a problem. There's a contradiction there. It's a logical contradiction. And here they tell you how they discover black holes. And again, it shows you that it's done indirectly. The way astronomers and astrophysicists detect black holes in astronomical observations is to look for light from ionized dust and gas being sucked into something so fast that it could only be a black hole. Again, it's an assumption which they're turning into fact. But now I got a problem with this. What do you mean dust being sucked in and I get the light? How can I get the light if it's sucked in? I thought a black hole was black because it sucked in everything in its vicinity and nothing was able to reach my eyes. So we had a problem. How did they do this? Well, it turns out that when they came out with this Chandrasekhar limit, they said, look, you know, black hole swallows everything in, it's zero-dimensional. So the astronomers said, well, we're out of a job. What do we look for? They said, well, we got to give these guys something to do, or they're all we're going to shut all the observatories down. So they came up with Hawking radiation. What is Hawking radiation? This is a quantum mechanics mechanism. Vacuum fluctuations cause a particle-antiparticle pair to appear close to the event horizon of a black hole. One of the pair falls into the black hole while the other escapes. To an outside observer, it would appear that the black hole has just emitted a particle. So we have to understand what they're saying here. They're saying space is made out of particles. You take a particle and an antiparticle, you put them together, and you end up with nothing. Take a ball, a black ball and a white ball, you put them together, and you end up with no ball. That's what they're saying, okay? That's space. Space can do the opposite. It can break apart the two and you have a particle and an antiparticle, a white ball and in this case, a blue ball and a red ball, right? The blue ball falls in. It doesn't matter which. It could be the antiparticle or the particle. Why does the red ball leave? What allows the red ball to leave if this area here is all full of gravity pointing to the center of the black hole? These people are saying, in other words, gravity stops at the event horizon. If you stand at the edge of the event horizon, you won't be sucked in. You're out of the gravity's range. If you take a step over, you get sucked into the singularity. But as long as you don't step over that line, you're okay. That's nonsense. Any star has an infinite radius, to use that term, for gravity. The Earth pulls on the moon a little outside our atmosphere. Imagine if you were just standing on our atmosphere and say, well, fortunately, gravity doesn't affect me because I'm outside the range of gravity. That's what they're saying. They're saying that the red ball can escape because there's no gravity there, and so it can just drift away. That's nonsense. It should fall also into the black hole. There should be any radiation coming out of a black hole. But if they did that, all the astronomers would be out of a job. So they had to create this nonsense called Hawking radiation. And now they look for these sparks out there. This is how Hawking represented in his book. You can see the antiparticle escaping to infinity. But gravity is not to infinity, just the particle escapes to infinity, right? This is what they observed. They observed gases being sucked into something, or nothing, whichever way you want to look at it. So the gases of a star are sucked in somehow, and they said, well, it's got to be that black hole. It's got to be something there that's pulling it in. All this mass, runaway gravity, it's pulling all that gases in. Okay, we all understand that. We say, okay, sounds reasonable. Okay, what else do they observe? They observe a star going around nothing in circles. They observe with their telescopes, they take measurements, they say, this star is moving quite fast, it's moving around nothing, we don't see anything in there. Now, it could be, some other object that we can't see, but they say, no, it's got to be a black hole because of the mass, and, it's just, this star just goes around it. And so they illustrate it like that. They say, that's what's happening. They're filling in the blanks. They're saying, that black hole, I'm going to put it in there so you can see why that star is going around. Well, but it's an assumption. It's an assumption based on the fact that black holes might exist. There could be something called a black hole. Well, I can just put an angel there. That's what I like to do. I like angels. They're moving the star around. And here I have an angel sucking all the air in there. I mean, I can put anything in. It's an assumption. Have I proven angels? No, it's an assumption. I say, let us assume there are angels. And if you concede my assumption, then I can explain to you anything. And that's what they're doing with a black hole. So what are the conclusions? Well, it's an irrational entity. First, because again, we don't know how many dimensions it has. We don't know if it's a black ball or a region. We don't know what mass is. They have never defined the word mass. People will argue for centuries with me. Mass and weight are exactly the same thing. And when I say that, people get so offended at me. But they've never been able to isolate mass from weight. Why? Because we measure them in the same way. You want to measure mass? In fact, that's what we had. The master is kept, of the kilogram, is kept in Paris. And it's a chunk of metal that weighs 1 kilogram. And we say that's 1 kilogram of mass. How do you know it weighs? Did you count all the atoms in there? Is it the quantity of matter? No. They weighed it. They said, this is going to be the kilogram. So weight and mass are the same thing because they have never been able to isolate one from the other. They don't count atoms. They don't count particles of matter. They measure. And when you measure, when you weigh or whatever do, you're not, then you can't distinguish mass from weight. And so these people have no definition for mass, and no one has ever seen a black hole. But if you read any popularization of the black hole, you will find always the same thing. They've proven it, it's a done deal, nothing to argue. And this is what should make you stop and think that something is wrong with mathematical physics. Okay, so this is what we got to answer. We have a star going around something or nothing. We have to answer, what's happening here? This is a real thing that they're observing in the sky. We got to, if it's not a black hole and it's not angels, what is it? We got to answer this question. Scientists can't avoid it. And the same thing here. If gas is being sucked into nothing, how do we explain this? What's going on out there in the sky, in the night sky? So that's what I'm going to answer now. I'm going to give you something. Again, I haven't come here to convince anyone. Came here just to give you an alternative so you can choose, make up your own minds. Okay? When you're in high school, you're taught that the light is an electromagnetic wave, okay? What is a wave? Well, according to Niels Bohr, early part of the century, of the 20th century, he said the electron jumps back and forth from the different energy levels. It drops to a lower energy level and emits a quantum of energy. And when it rises, it absorbs a quantum of energy. So that's what you're seeing here. That's the quantum leap there, quantum jump. And when it falls to an energy level, it emits a wave, it emits a quantum of energy, and that's the wave that you see running out there. It's the electromagnetic wave. And it's made out of an electric field and a magnetic field at 90 degrees to each other, okay? What are the problems with this setup, with this thing that they teach us in high school? There's no such thing as a wave. Wave is what something does. A flag waves, but I can't say a wave waves. Wave is what something does. You can say the water wave, but you can't say the wave waves. What's the object that's waving? Well, they tell you there is no object in the case of light. And some people say, well, it's the ether that's waving. And some people, you know, there's a big fight on whether there is something called an ether out there. Most people believe there's no such thing. But the point is, there's no such object as a wave. Wave is a verb. It's not a noun, okay? And they've turned it into a noun in physics, or in mathematics, really. Second, the wave is 2D. Each one of the components, the fields, are two-dimensional. And there's a problem with that because you have situations like the photoelectric effect, where Einstein, in fact, showed that the quantum packet is hitting an electron and taking it out of its orbit and causing electricity to flow. If you point a light to a shiny metal plate, it emits electricity. There's a current flowing. And they're saying what's hitting it is light, and it's forcing the electron beads to flow from one atom to another, and that's current. Well, we had a problem with that because then if the wave is two-dimensional, how does it interact with three-dimensional objects? So we can't fit the two-dimensional wave or the two-dimensional fields in with three-dimensionality interaction. That's where the problem is. Orthogonality, the electric field goes 90 degrees to the magnetic field. Why? Why would it? In fact, when you're in high school or college, they show you something like this. Let's see, loosen it up, right? They go up and down, and they show you a transverse wave, a wave that moves up and down perpendicular to the direction of travel, right? They go something like that. But there's two conditions. First, this has to be tied. If this is not tied, I can't produce that. That's the first issue. So in order to do this, I got to tie one end on one side and the other one I got to hold on to. Then I can shake it. If this is not tied, I can't do it. Then why would the wave travel rectilinearly? Why does light travel in straight lines? You can't do it with the transverse wave. And why would the electric field travel perpendicular to the magnetic field? Is it just God? That's it? And then we have the problem, where does the wave begin and where does it end? Here you have the Andromeda galaxy, and you have an atom emitting a wave to your eye. Is it a little boat that travels, or is it an extended object that extends all the way from there to your eye? Which is true? Which is the correct representation? Well, they like to talk about packets, discrete packets. They want to show you that it's these little balls that are coming to your eyes, ta, 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 like a machine gun shooting bullets at you. But that's what they illustrate. They illustrate a continuous wave. Where does the wave begin? Does it begin here and end there? How long is a wave? Where do we chop it off? See the problem? So they talk about continuous on the one side, and they talk about discreteness on the other. And they merge both into the wave packet. Wave packet is both discrete and continuous. So again, they cover all the bases. They call it duality. They say, yeah, you got to accept that it's both. See, we can cover every base with this. This is better than God. You know, we cover everything. And so what do they end up with? Well, this is the Penrose wave packet. This is science here now, folks. Please don't laugh. That's Cupid's arrow and got tangled with some serpentine in there. This is what they illustrate for the wave packet. What is a wave packet? Is it a wave, continuous wave, or is it a packet, a discrete packet? It's both. And of course, when they do it that way, it's very hard to challenge. So what are we replacing this with? We're saying that what they've been looking at all these years is a rope. Now we can explain all these features of light. Why is it straight? Because the rope is pulled tight. And I'll illustrate that here. little rope that I always bring. If this is pulled tight, then you can imagine why there's a straight axis. Now you can also see why the electric field, which we call a thread, it's a physical object, a field is not a physical object, goes at 90 degrees to the magnetic field, which is, again, a thread. There's two threads. It's what DNA imitated. DNA imitated light. That's why we have all these things like collagen. They're all extended objects like a rope. They're all rope-like features. And here you can see, why it's straight. It's pulled tight. And how do we produce light? Well, we torque it. There's a torsion. It's a three-dimensional wave, not a two-dimensional up and down wave, but a torsion. So now you have an atom. In fact, I've illustrated here in the next slide. You have an atom. Here's the rope. Now you know why it's called the rope hypothesis, by the way. And you'll see it here. The two atoms are tied. It binds any two atoms in the universe. The atoms are vibrating. They expand and contract. They're little balls of yarn. You can think of it that way. When they expand, they twist the rope, and now you have a torsion traveling to the other atom. When it contracts, same thing. See, the good thing about a rope, it goes both ways. The signal goes both ways. While you can see me and I can see you at the same time, like that, it's because it's a rope that's connecting these atoms, not something that I send to you and you send to me. See the difference? There's a difference in the concept here that we're trying to show. There's an equation that says c, which is the velocity of light, is a constant. It always travels at 300,000 kilometers per second. Why? Well, c, little c, in other words, the velocity of light, is frequency times wavelength. That's the f, and that's the lambda there. Frequency times wavelength. If you increase the wavelength, you make it longer, you have smaller frequency. And if you increase the frequency, if you decrease the frequency, you have to have shorter wavelength. And this is the equation of a rope. If you take any rope, right? I'll show you this real quickly here. I can tighten this many times, same amount of rope. And now you have more links per unit length. I can undo this and you can see what happens. Now the links are longer, but you have fewer links. That's frequency times wavelength in the model of the rope. This is the equation of a rope. That's why light travels at a constant speed. Frequency can only do it at the expense of wavelength. Only. A rope explains this equation. So what's the difference? Quantum mechanics talks about discrete particles, and we're saying every atom in the universe is interconnected. They're all connected to each other. Now we can explain gravity, for example. For example, one thing that quantum mechanics and I explain is the force of pull. How do you pull with two particles? How does one particle pull on another? There's no mediator. You have to use angels. You have to use magic. And here we're saying that the atoms are interconnected. There is a rope there that's connecting them. We don't see the rope because you can't see atoms. Much less can you see this electromagnetic rope, because we're talking about something so thin. You can't see it. Besides, you would need light to see light, because that is light. See? So people ask, why can't we see it? You can't see it. These are invisible threads that are connecting every atom in the universe, and that's the mechanism, the medium through which they send light. They send the torsion signal. Okay, we can explain gravity. Here we see the sun, the earth, and the moon. They're all connected. Now we can see why the moon goes around the earth and the earth around the sun, because they're all connected. Why doesn't the moon fly away? They've never been able to explain this. They can explain it with two objects. They can say we have a gravity well. This is what Einstein explained. He says we have a gravity well. The sun weighs down the canvas of space-time. We don't know why it weighs it down, because you need gravity for that, but we'll concede that. Okay, so the sun weighs the canvas down, the trampoline, your couch. You sit, you sink the couch, and now the ball rolls around you. Fine, no problem. Why do we have third objects that don't follow that? If you look at Uranus, it weighs down the canvas, and it has its moon go around it, but it doesn't go around in the same direction. It goes over the poles. Why would it do that? Uranus would have to weigh the canvas sideways. Then you have the case of Pluto. Pluto it has Charon, which is its moon, and faces the sun like a bullseye pattern, like you're seeing right now from me. then Pluto would have to push the canvas in my direction for you to see that bullseye pattern. In other words, you can't do it with 3 objects. And they know, the mathematicians are well aware of this problem. It's a 2-object system, the one that Einstein explained. He can't explain 3 objects. There's no way. Because you would have to make it ad hoc, put it by finger, because there's no other way to explain it. You can't explain it with math, for sure. Okay? So we have a problem there. Okay, so what do we do with this? Well, we're going to explain magnetism, because I'm going to show you a different version of this, of what causes these black hole phenomena. I'm saying these have to do with magnetism, not with gravity, have nothing to do with gravity. According to the thread theory, or the rope hypothesis, we take any 2 atoms here, right? One of the threads comes loose, begins swinging around the atom. We take a row of them, we have a bunch of threads going around each other. Now we have a wall of threads going around. Now we can explain electricity and magnetism. Current is flowing upwards in here in this vision, and the magnetic field is going sideways. We verify this in the lab every day. The magnetic field travels perpendicular to the electric field. Well, here's a visual representation of that using the rope hypothesis. How do we explain magnetism with this? Well, we have these threads, the ones on the top moving in one direction in a magnet, and the ones on the bottom moving the opposite direction. Okay? So you see the flow of all the threads on the top part of a magnet moving in one direction, and the other ones on the other side. This can explain why if we throw iron filings over a magnet, it gives you those patterns. It gives you a pattern because something is moving in there, in that so-called magnetic field. I can show you this here. If you put a magnet into water and you have all these iron filings floating in there, you will see that over time, hopefully you'll see it there, it collects all the iron filings. If nothing is moving there, they would just stay where they are. But something is moving, something is drawing these iron filings in. Something is moving. That magnetic field is something in motion. We're saying it's the threads that are moving and collecting all these iron filings and keeping them close to the magnet. And how does this produce attraction and repulsion? Because we have to explain how a magnet attracts another if we're going to explain magnetism. Well, here we have a vision of that. We have 2 magnets. They're both facing in the same direction. We have north-south, north-south, the traditional north-south, north-south. And the ones at the top are all flowing clockwise. The ones on the bottom are flowing counterclockwise. So what happens? As the top ones from the first magnet come down, they collect the ones from the top of the second magnet, which are coming up. So we have this situation. Okay? And the ones on the bottom do exactly the opposite. And so now a magnet attracts another magnet. And the closer they are, the more threads that intervene, the faster is the attraction, and that's what we verify in the lab. So this is a different mechanism than what you've been taught in high school. Repulsion, we turn the magnet around, and now we have one clockwise, the other one counterclockwise. Now they're hitting each other. Now they don't like each other on the top and on the bottom. So now you can't put them together. The closer you have them, the more threads that intervene, the harder it is to push them together. No particles, just threads moving around a magnet. How does this explain now black holes? We got to explain now the black hole. This is a galaxy when we factor the magnetic field, the gazillions of threads coming out of every atom that comprises the magnetic field. A galaxy has gazillions of stars, each one with gazillions of atoms. A bunch of those are excited and they create the magnetic field of the galaxy. So the galaxy has a magnetic field, and each star in it has a magnetic field also around it. So you have these little charged balls in this humongous galaxy, and both are charged. So how do we produce now these motions, these fancy motions? If you take a charged ball in the lab, you can do this in the lab, and you run it through a magnetic field, it turns in circles. Now we can see why the star would go around in circles around nothing. Because that ball is going around nothing, we can do this in the lab. We don't need mass, we don't need gravity, because this is not a gravitational phenomenon. I'm saying that what's happening here is you have the magnetic field of the entire galaxy. In this case, it's sweeping through the center downwards. It doesn't matter. Different galaxies, depending on how you look at them, they could be upside down or whatever, as far as their magnetic field. And this is the effect. You have a field coming down, and it forces a charged particle, and we'll call it a charged ball. It forces it to go around in circles, around nothing. So this is what you would observe. You say, oh, what's in the center? Why does the bee go around the flower? Because of the mass of the flower. No. It's a wrong conclusion. And there I illustrated here, you see the little stars going around in circles. This is what we would observe through our telescope. We see there's nothing there. All we see is a star going around. Yeah, because the magnetic field is invisible. We don't see the magnetic field of the galaxy. What they do see from every galaxy is the jets. They call them jets. They think it's throwing plasma out of the center. Again, if every galaxy has a black hole in its center, it would not be emitting anything. It would be swallowing everything in. You wouldn't see anything. But they had to create the jets, so they say it's jets. Those famous jets, that's the magnetic field going around the galaxy and forcing charged objects, such as stars, to go around in circles. And sure, you would not see anything in the center of that, circular motion. And here we see a magnetic field swallowing gases, in this case smoke. This is a magnetic generator, and you can see how it's sucking up the smoke. What are the particles that we see out there in space, these gases? A star has suddenly all these gases coming out of it, and they say, where's it going? Well, it must be a black hole or an angel, whatever, It's going in there somewhere. Well, we're saying, look, it doesn't have to be anything. You can have, in this case I drew it this way, you can have the gases of a star being sucked into nothing because it's all drawn by the magnetic field of the galaxy. So you would not see an object swallowing it. It just forces a star to lose the gases off its surface. Okay? So again, all I'm trying to show you is that there is a different way to give explanations to these same phenomena, and you surely can't do it with the black hole, because the black hole has not been defined properly. We don't know how many dimensions it has. We don't know what it's made out of, and we've never seen one directly. So it's an assumption turned into a fact. I'm going to go now briefly over dark matter. You hear about this as much as you hear about black holes. Dark matter is the latest craze. What is dark matter? Here's our solar system. Okay, Mercury goes real fast around the sun. Pluto takes 248 years to go one time around the sun, very slowly. So here we have this little planet close to the sun. It goes real fast, and the one out here goes very slow. If you plotted, the speeds of each of the planets around the sun, the orbits, that's the curve you would get. You can see that as the radius increases, the orbital velocity decreases. Okay? So the orbital velocity is always slower the farther you get away from a planet. That's not what happens with a galaxy. It's called the galaxy rotation problem. Galaxy has a different curve. This is the one we expected, the one on the bottom, which resembles the one in our solar system, but that's the one we get. The farther you get, the speed is increasing or staying the same. And they cannot explain this. They say, how can this possibly be? How can we get stars on the outside of a galaxy to travel so fast that they keep up with the ones on the inside? It's like the whole thing rotates like a carousel. The buggy's on the inside as fast as the horses on the outside. They all go at the same time, so to speak. It's not exactly like that, but think of it that way. What explanation do you give for this? Well, they created a theory. It's called the dark kilogram theory. The dark kilogram theory says that, if you have to match the observed with the predicted, what you do is you put kilograms in there. And so they put kilograms wherever they needed it. They said, well, we need it here. If we put it here and here and here, then we can explain this. So they created this dark kilogram theory. They call it the dark matter. I like to call it the dark kilogram because have you ever seen a kilogram? What does it look like? Well, that's what dark matter looks like a kilogram, more or less. So they put this kilogram and they said, well, if we put it here, then we can make it go faster. We don't put it here, we make it go slower. So they just fit all this dark matter wherever they needed it. It's an ad hoc invention. They said, we can't explain it. This is what we observe. How do you explain it with math now? What equation can we use for this? And so they invented this variable called dark matter. And so they put it wherever they needed to create that curve. They need to just explain the curve, and they can't explain it. So they said, well, we're going to look for it, but meanwhile, this is the distribution. And if you look at a galaxy, yeah, they did it on the outside. Usually it's on the outside of a galaxy. The question is, why doesn't this dark kilogram invisible nonsense exists between the Earth and the Moon. Don't we have kilograms here as well, dark matter between the Earth and the Moon? And if we did put it in there, then all the equations would be out of whack. Newton wouldn't work, Einstein wouldn't work, nothing would work. We can't put it between the Earth and the Moon, any dark matter, because then we wouldn't be able to use our equations for our rockets or whatever. So they poured it on the outside of a galaxy. It's always on the outside. That helps us explain the curve. Now they're looking for it. It's invisible, it's translucent, it's dark. It doesn't block out any stars in the background, but it exists, and we're looking for it, and you're paying for it. That's the important part. I gotta say that. This is a web. It's made by a little spider here on Earth. And that's what we're saying that we're looking at. All the stars in a galaxy are interconnected. We're going to put this web on top of a galaxy. Okay? So we put it on top of the galaxy, and what are we saying? We're saying all the stars are interconnected. Now we can see why the galaxy rotates at the same time, more or less like a carousel. Because if every star is interconnected, and on top of that you have the magnetic field giving more integrity to the galaxy, now you can see how it all rotates like a carousel. We can explain that part at least. We don't need any dark matter for this. Okay? It's a simple explanation. In other words, if every atom in the universe is interconnected, then we can explain why the galaxy rotates the stars on the outside at the same speed as the one on the inside. And finally, I'm going to do a little bit of Big Bang. Big Bang is the moment of creation without God. There's no God here. It's just a self-creation. And what is the problem with Big Bang? The problem with Big Bang is that how do you identify the thing that was there before the explosion happened? What was there? You start out with what before you end up with the universe? How do you create matter from nothing? So we all have a little bit of problem with that, right? So they don't answer that question. But then they tell you that all these universes, all these little cups, here's the beginning, right? And this is time. We live in parallel universes, and they're all interconnected by wormholes. Those are the little curlicues you see there. They're all interconnected. Zero-dimensional entrances, one-dimensional wormholes, right? Let's understand that. I drew it as two-dimensional because I can't draw one-dimensional things yet. So these universes are interconnected by wormholes. The question is, what is the black stuff that separates all these universes? This contains space, time, and matter in there. Space, time, and matter. It's all in there. What's the black stuff then? It gives shape to space-time and to all these space-time. What is the wormhole traversing to get to the other universe? What is that medium? Thought? I mean, I don't know. That's what they have to answer. These are the questions. What physical medium contours, right, give shape to space-time, and how is matter self-created? I mean, here we don't have God. Even God would have trouble creating matter, but without God, I don't know. It's beyond my imagination. So how do you answer these questions? How do you answer what physical medium contours and how is matter self-created? Well, here we have a couple of testimonies. One is from Hawking, again, from his brief history of time. It is impossible to imagine a four-dimensional space. You can't imagine, you just have to accept it on their word. Okay? In general relativity, it became meaningless to talk about space and time outside the limits of the universe. So they're not going to answer that question, what that black stuff is, because it's a meaningless question. They say it's an unscientific question because they can't prove to you with an experiment what that black stuff is. But this is a conceptual issue. They can't start their presentation until they tell me what that black stuff is, because they're going to run wormholes through it. They're going to separate all these universes from one another with this whatever thing it is. They have to tell me what that black stuff is. To say that that's beyond the reach of science, it's just saying, we're not going to tell you, but listen to our theory. You're going to have to accept it on the basis of our authority. Questions such as what is beyond the edge of the universe, or what is the universe expanding into, are as meaningless as asking what is north of the North Pole. Now, what is north of the North Pole is the North Star. Sirius, or some star out there. There is a north of the North Pole. What is north of space, or space-time? Can we imagine, are we talking about a ball and there's something out here outside of our universe? And then again, what separates our universe from the other? We have to answer these questions. We can't just say, well, we can't answer that. That's a conceptual issue. And another fellow said, such questions as, is the universe finite or infinite, or what caused the universe, are false, cannot be answered because the point of view from which such questions arises does not really exist and is unattainable. In other words, they'll never answer that question because creation, self-creation, is beyond words. It's got nothing to do with science. How do they create stuff from nothing? Well, I already gave you a little insight earlier. Said, you have particle, antiparticle, and that's more or less how they explain the creation of something out of nothing. Space is made out of particles. Antiparticle and particle, you separate them, and now you have particles, which before was space. You put them together, you create nothing, space. Okay. At the Big Bang itself, the universe is thought to have had zero size. Great. What was outside of it? We don't know. In quantum theory, particles can be created out of energy in the form of particle-antiparticle pairs. So now we can create energy from that. That means we have something, which is called energy. But that just raises the question of where the energy came from. Okay, look at the explanation. The answer is that the total energy of the universe is exactly zero. Why? Because we have positive energy, well, negative energy. That's a mathematical calculation. That's minus E plus E goes zero. What does that have to do with physics? They're saying that we have zero energy. That's the starting point. Now we separate positive from negative energy. We create matter. We have matter, antimatter, and now for some reason we ended up with matter, which is us, right? And the antimatter maybe went to another universe. I don't know. You see the problem? These are all irrational explanations. We're not attacking the math. We're not saying, the math is wrong. We're saying the explanations, the physical interpretations they give us. The physics part is absolute irrational. It's not wrong. It's not incorrect. It's irrational. They cannot, they tell you, we have Richard Feynman. He's a 1965 Nobel Prize winner. And he says, no one understands quantum mechanics. That's what he said. We're talking about 1965. By that time, quantum had been around for 50, 60 years. Arthur Eddington, guru of mathematics of England, he said, there's only two people in the universe who understand general relativity, and he was referring to Einstein and himself. So nobody understands these theories. They can't. There's no way. They cannot explain them to you in a rational manner that you would understand. They say, you want to understand it, you got to go to college and learn math, then you'll understand it. Then you'll be brainwashed in the right way. It's nonsense. It's all nonsense. Here's another testimony. This is from Brian Greene in The Fabric of the Cosmos, a popular documentary. He says, empty space is far from empty. In fact, it is teeming with activity. Particles constantly are popping in and out of existence. They erupt out of nothingness, quickly annihilate each other, and disappear. So it's all magic. I call it mathematicians because it's all magic. What is this? Is this science? This is physics? This means that they have the wrong hypothesis. They have the wrong starting material. And they have to cover for that with these theories, these mechanisms. The quantum mechanics empty space is not that empty. Another from Leo Susskind. It is full of fluctuating fields, full of sorts of jittery things going on. So this is the establishment's version of how particles get created from the void, from nothing, from the vacuum. Antiparticle, particle, they separate, and you put them together and you create nothing. Okay? Well, we do it a little different in our physics group. We say in physics, space is synonym of nothing. What is nothing? Well, we have to define it. We have to say space, that which has no shape. That's what space is. Nothing is that which has no shape. So something is that which has shape. Nothing is that which has no shape. They're antitheses. One is the opposite of the other. Now we can use these words consistently. Now I can talk to you in a rational manner. When I talk space, I'm talking about nothing. When I talk to you about an object, I talk to you about something that has shape. So space cannot spontaneously acquire length, width, and height all by itself and turn into a physical object, and an object cannot spontaneously lose length, width, height, and become nothing. Now we can all understand. We can say, look, here we have a something, and it cannot lose length, width, and height suddenly, all of a sudden, spontaneously, and become nothing. This becomes this, nothing. You can't do that. That's magic. That means I'm not going to explain it to you. I'm not going to explain to you the process. I'm just going to tell you it is, and you get to accept it. And that's what they're saying. So the conclusion, matter has always been there. We've never created the universe. It's never going to die or disappear. Matter has always been there. Matter cannot drift past that which has no boundaries. If space is that which has no shape, there's no boundary to cross. Not even God can escape that which is not a medium and has no shape. Space is the largest prison never built. Space is nothing. And we cannot convert something into nothing, nothing into something, and nothing cannot cross that which has no boundaries. Now we can make sense of this. There is no Big Bang. That's it. Different worldview.